Good morning. We will begin with a summary of lecture 10, and then as you recall, we did a fair amount of discussion on linear interpolation. We will look at the next aspect of a fractional sampling rate change, which will introduce for us all of the elements of the multirate processing that we are interested in doing. The multiplexer and demultiplexer, as I mentioned, are common blocks in communications. Now, where do they find a role in DSP? It is in the context of multirate DSP. We will introduce that. Then the complete toolkit of what are all the building blocks that you have. You have the building blocks from DSP, the LTI blocks. Then you have these two linear but not time invariant blocks, the upsampler and the downsampler, and then how all of them fit together. We will look at it with a series of examples. So, let us begin with a review of yesterday's lecture. So, the basic building block that we have is a upsampler. The two basic building blocks, we have a upsampler. We will label this portion of the processing as upsampling. It is insertion of L minus 1 zeros between two successive samples. However, because of the number of samples present, you have actually effectively increased the sampling rate of the system. Then if you cascade it with a low pass filter H of Z, then the specifications of this filter is that it is an ideal low pass filter with omega c equal to pi over L. It will remove all images outside of minus pi over L to pi over L. Such a filter we would refer to as our interpolation filter, okay, ideal interpolation filter. So, that means you will know exactly what we are referring to, upsampled by a factor of L. So, the combination of these two operations is the interpolation operation. So, interpolation for us is not a single step, it is the insertion of zeros, replication of spectrum, then filtering to remove the additional copies of the spectrum. So, this is one element that we have studied. So, upsampling followed by filtering. Then the corresponding blocks that we have for the downsampling. So, the downsampling block denoted by a down arrow and M, you have your input output. This is referred to as downsampling, this portion. Reduction of the number of samples, throwing away M minus 1 samples, downsampling process. And as you recall, we also said that this also can have a filter, in fact will require a filter if you want to guarantee that it does not have aliasing. So, H of Z, this would be an ideal low pass filter with cutoff pi over M, with cutoff omega c, cutoff is pi over M. This we would call as the anti-aliasing filter, AA filter, and then you have the input to the anti-aliasing filter, and this whole process alias free downsampling or alias free decimation. So, that alias free comes on because you are and you are exploiting a sufficient condition which says that if I limit my spectrum to pi over M, then I am so this is alias free downsampling. And keep in mind that we said that this is a necessary and sufficient condition for baseband signals. So, we are not dealing with the cases of band pass sampling, because band pass sampling can be handled and should be handled differently. Then the after we have this insight, the observation or the point that we were discussing quite at length, and there were several questions after class, very good discussion that we had, was what is the interpretation of linear interpolation. Linear interpolation, we said, can be understood as a upsampling by a factor, whatever is your requirement, upsampling by a factor of L, and then you are using an interpolation filter, but the interpolation filter is not the ideal interpolation filter. So, in this particular case we used an interpolation filter which had a triangular response. So, basically you had and depending upon how many samples, the value of L, you will have the size of your interpolation filter. So, basically it is a linear, this is what gives you the convolving the upsampled signal with this. So, this is my modified interpolation filter and nothing specified, nothing says that you have to have an ideal low pass filter. You can have different filters, but you have to know what are the consequences of that. So, basically this combination is what we called as linear interpolation. Okay, so, this is xi prime of n. Xi of n, you can think of it as ideal interpolator. This is xi prime, which is something which is like the ideal interpolator, but maybe has some deviations. Okay. Now, the concluding remark was that linear interpolation, if you have critical sampling, that is if you are exactly at Nyquist, then it actually distorts the signal. So, linear interpolation is a good option only when you have the input signal is already oversampled. So, is a good option if x of n is already oversampled with respect to Nyquist. So, then what you will find is that you can get rid of the images and whatever distortion occurs is minimal and does not cause a problem. Is already oversampled with respect to Nyquist sampling frequency. Okay. So, that is the key element. Okay. Now, let us build on what we have discussed in the last class. Several useful results by way of a review. Let me just ask you to look at this particular block. Downsample by a factor of 3, upsample by a factor of 3. Okay. So, this is x of n and the output is the same as x of n multiplied by the comb sequence C3 of n, and if you want to have a visualization of that, it's good to sort of keep in mind what exactly we have done. So, if I have a signal, some signal which I sample, so that is sample number 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, some signal that has been sampled. Okay. The downsampling process says that I am going to retain only a few every third sample. So, downsampling process will retain this and this. Okay. So, every 2 samples in between have been thrown away. So, then the upsampling process says you will restore 0 valued samples in between L minus 1 zeros. So, the 0 valued sample is here, these are the samples. So, basically the comb sequence keeps in this case every third sample, and the rest of the samples are set to 0. And in yesterday's discussion we had some variants of this. We said that if I can advance this by 1 unit of time, then followed by the downsampling by a factor of 3, upsampling by a factor of 3, and then followed by a delay Z inverse, we said that the output would be, if this is x of n, the output would be x of n multiplied by a comb sequence, but shifted by 1. So, it is basically a different subsample sequence C3 of n minus 1, and you can sketch what that looks like, and also you can modify this block to get x of n C3 of n minus 2. Basically, it will be z squared and z minus 2 to get the so, please fill in this draw the figure. Okay, you can try it out. That is just a simple exercise. Okay, now comes a very interesting element of putting all of these pieces together. Like in the last class we talked about it in the context of a comb sequence with keeping every other sample, or we split into odd and even sequences. But let us just look at a slightly different case. We take m equal to 3, that means upsampling, downsampling both are, so L equal to m equal to 3. So, the blocks that we have. So, the first branch that we have has got downsampling by a factor of 3, upsampling by a factor of 3 and the output comes out. Okay. Now, the second branch, I am going to introduce an advance operator, downsample by a factor of 3, upsample by a factor of 3, and this will get added to the other signal. Please note the direction of the arrows, very important. Okay. So, the second branch gets added, we need to insert something, we need to insert a delay operation here, Z inverse. So, there is a, okay, and then a third branch where we have another advance operator followed by downsample by a factor of 3, upsampling by a factor of 3, a delay operation, okay. So, let us analyze what we have. So, here is a system where there are 3 branches. If I can, this is a linear system, so I can break it up into 3 parallel things which are getting added. So, the first branch is downsampling by a factor of 3, upsampling by a factor of 3, that as we looked, as we said in the previous case, that is x of n, C3 of n. The second branch, input comes, goes through one delay unit, downsampling by a factor of 3, upsampling by a factor of 3, Z inverse. So, basically at the output I have x of n, C3 of n from the top branch, that is what is coming from this side. Now, coming from this portion, the second branch is a plus x of n, C3 of n minus 1, and just for a moment follow along on the second branch. If I follow from the input, there are 2 delay elements, so that is z squared, downsampling by a factor of 3, upsampling by a factor of 3, and then passing through 2 delay elements. That turns out to be x of n, C3 of n minus 2. Okay. So, take x of n out common, C3 of n, C3 of n minus 1, C3 of n minus 2, basically comb sequences interlaced, you will get back x of n. Okay. So, if this is x of n, the output will turn out to be x of n, and I think you can either draw it or visualize it, whichever way you want to justify. Okay. Now, just want to make sure that you are comfortable with this. So, let me give you a task which I am sure you will find interesting, and copy. Okay. So, I am going to modify this figure a little bit and then ask you to work with this and then let me know what is the answer. Okay. So, delete a few things. Okay. So, I am going to modify this figure. So, the upper branch is downsample by a factor of 3, upsample by a factor of 3, and is going to now, that is not going to be the one that is producing the output. I am going to feed it downwards to another delay element, z minus 1. Okay, let me quickly clean up my diagram. Both sides, left and right, I have now have delay elements. Okay, so this is a plus sign, and okay. Now, the second branch turns out to be z inverse, downsample by a factor of 3, upsample by a factor of 3, comes to the output, goes downward, that means through another delay element, and then comes out. The third branch goes through 2 delay elements, downsample by a factor of 3, upsample by a factor of 3, goes out. Okay. Can you tell me what the lowest branch will be? What will be the effect of the lowest branch? Or let's take the other one. The upper branch is very easy to see. It is x of n, downsample by a factor of 3, upsample by a factor of 3. That means it is this first sequence, okay, which has then been delayed by 2 units of time. Okay. Now, go through the second branch. Second branch effectively had one advance operator and one delay operator, but now has got 2 delay elements. Okay. So, if you look at it carefully and then analyze, you will find that this one also turns out to be that you have to do it systematically. Basically verify that if this input is x of n, you still get the interlacing property, all the 3 downsample sequences get properly interlaced, the output turns out to be x of n minus 2. Please do verify, probably it is helpful if you define a sequence x1 of n, define another sequence x2 of n and a third sequence x3 of n. So, the output is x3 of n plus x2 of n minus 1 plus x1 of n minus 2. Okay. So, you can write down the expressions and make sure that you are comfortable with this result. Then let me proceed on to the fractional sampling rate, because this will also teach us and give us a lot of interesting insights. So, fractional sampling rate change, it is an example, but it also gives us a lot of the insights into what we are trying to develop as far as the multi-rate framework. Fractional sampling rate change. So, I have a signal x of n which is sampled at 12 kilohertz, okay. Want to transform it into x prime of n, which is basically x of n, but at a different sampling rate at 16 kilohertz, So, yesterday we did say that I can visualize this as a system where I do a downsampling by a factor of 3 and then upsampling by a factor of 4, which means effectively I will get 12 kilohertz, downsampling by a factor of 3, this gives you a 1/3 multiplication factor of the sampling rate, upsampling by a factor of 4 gives you a multiplication by 4, this gives you 16 kilohertz, that gives you the target that you are looking for, right. And of course, we can do the upsampling first. You may say, well, you know, I heard somewhere that upsampling should be done first. So, do the upsampling by a factor of 4, downsampling by a factor of 3. Now, look at the overall sampling rate. This is also at 16 kilohertz. Both are what I would like to do first is analyze these 2 structures, because it introduces for us a very important concept in multi-rate signal processing, especially if we try to interchange the blocks. One of the things that we want to focus today is when am I allowed to interchange these 2 blocks. Obviously, downsampling and upsampling are both time variant blocks, and therefore, interchanging of time variant blocks is generally not permitted. So, is there a possibility, you know, are these 2. So, let us analyze this a little bit, and it will give us a lot of insight. So, let me label the signals. This is x1 of n, x of n, this is x1 of n, this is x1 prime of n. So, can you write for me the time domain expression? x1 prime of n is x of 3n, that is the downsampling, okay, that is equation 1. The second equation says that x1 of n is equal to x1 prime of n by 4 if n is equal to a multiple of 4 is equal to 0 otherwise, okay. Now, can you rewrite for me the expression for x1 prime of n. So, x1 prime of n is equal to x of 3n. So, can you help me write this equation? So, x1 prime of n by 4 will be x of 3n by 4, whatever is the argument multiplied by 4. Okay. What is the condition? x1 of n is x of 3n. Okay. So, basically what we are saying is this condition will hold if n is a multiple of 4, which is the same as n is a multiple of 4, right. But okay. So, equal to 0 otherwise. Actually I just have to be a little bit careful here. X1 of n is x prime of n by 4, that is the downsampling operation. I now have x1 prime of n, which is x1 prime of n is x of 3n. So, x prime of n by 4 if n is a multiple of 4, that is x of 3n if n is a multiple of 4, if n is a multiple of 4, yeah. I have not changed the condition. So, yeah, that is in this particular case, just be careful. Okay. So, basically x prime of n is x of n is x prime of n by 4 is n is a multiple of 4, and x prime of n by 4 is nothing but x of 3n by 4. Okay. So, this is the final expression for x1 of n. Now, let us look at this sequence. Same input x of n, let the output be called as x2 of n and the intermediate signal x2 prime of n. Now, x2 prime of n is x of n by 4 if n is a multiple of 4, n is a multiple of 4, 0 otherwise, and x2 of n is equal to x2 prime of 3n downsampled. So, now if I substitute x2 prime of 3n, give me the expressions, it will be x of 3n by 4, the argument of the of x2 prime has to be a multiple of 4. So, if 3n is a multiple of 4, if 3n is a multiple of 4 equal to 0 otherwise. Okay. So, x2 of n. Now, please compare the two expressions that we have obtained. Given the fact that 3 and 4 are prime, relatively prime. So, therefore, n being a multiple of 4 and 3n being a multiple of 4 are exactly the same condition. So, there is nothing different between the two terms. So, effectively x1 of n is equal to x2 of n. Okay. A very important observation that needs to come along with this one. Is this true in general, that I can interchange? What this is telling me is I can do the downsampling followed by upsampling or the other way. So, let us quickly make sure that we have this very clear in our minds and there will not be any confusion as far as this thing is concerned. So, let us take this particular case, the general case. Downsample by a factor of m, upsample by a factor of L, upsample by a factor of L, downsample by a factor of m. Okay. So, special case number 1 is the case where L is equal to m. And of course, I will take special case number 2, which is L not equal to m. Okay. So, right off the bat, so that means it is downsampling by a factor of m, upsampling by a factor of m. What is the output? X of n Cm of n multiplied by a comb sequence. Okay. Now, what if I upsample by a factor of m, what does it do? If I have a inputs, if I have a sequence where I have the following samples, okay, if I have these as my samples, now upsampling by, let us say L equal to m equal to 2, it does the following: it inserts 2 zeros between every set of samples, and then downsampling by a factor of 3 removes those 2 samples. So, what I get at this point is x of n, input x of n, output x of n. So, clearly when L and M are same, they cannot be interchanged, because one of them, here there is no loss of information, no loss of information. On the other hand, the case where L equal to M and I do the downsampling first, there is loss of information, loss of information. So, I have to be very careful with this. So, obviously the first observation is that if L and M are the same, they cannot be interchanged without the penalty that you will have to pay. Obviously, this is a case where L and M are not the same. Now, can I make the general assumption that I can always interchange when they are not the same, and we will work out in a very careful manner how that is supposed, such a question is supposed to be answered, but maybe just let me start by giving you the framework. So, the way we would analyze is that let us say that this is x1 of n and this is y of n, x1 of n, y of n. So, x1 of z would be 1 over m summation k equal to 0 through m minus 1 x of z power 1 by m w m k, correct? That is the downsampling operation. Yes. If x of n not band limited to pi over m, that is a good point. Yeah, because if you have not band limited, if you are band limited to pi over m, then the first step does not produce for you any loss of information, and yes, the signals are different, but you can still hopefully recover the information that is of interest. That is a good point. So, x1 of z is given by this, y of z is x1 z power L, that is the upsampling process, okay. And in this case let me write it as x1 z power m. So, I have to go back to my equation number 1 and replace z with z power m, okay. Please be very careful, I am replacing z, wherever z occurs I replace it with z power m. So, this is equal to 1 over m summation k equal to 0 to m minus 1 x, there is z power 1 by m, I am going to replace z with z power m. So, that means z power m by m, which is z power 1, and then I have w m k, this is y of z, okay. Now, notice that there is scaling, amplitude scaling is there, multiple copies are there, copies, they are spectrally shifted. The only thing different from a downsampling process is that there is no scaling of frequency. So, spectrally shifted. So, this combination of scaling, copies and spectrally shifted is by the comb sequence. So, it is straightforward, or we can go back to the earlier lectures and you can confirm that this is nothing but x of n Cm of n, x of n multiplied by the comb sequence. If I call this as, let us call it as x2 of n, and this output as y2 of n, x2 of z is x of z power m, I am choosing L equal to m, x of z power m, y2 of z is the downsampling process, 1 over m summation k equal to 0 to m minus 1 x2 of z power 1 by m w m raised to the power k. Basically I have written down the equation for expression for a downsampler. Wherever there is in x2 of z, I am going to have to replace x of z power m. Okay. That means the argument of x2 of z is going to be raised to the power m as an argument of x. 1 over m summation k equal to 0 to m minus 1 x of z power 1 by m w m raised to the power k, this whole thing raised to the power, let me use a different color, maybe easier to see that, this whole expression, okay. Now z power 1 by m raised to the power m gives me x of z, omega wm raised to the power k is e power minus j 2 pi over m multiplied by k. Now if I raise it to the power m, m and m will cancel, this becomes coefficient equal to 1. So this effectively becomes 1 over m summation k equal to 0 to m minus 1 of x of z. You add it m times and then divide by m, trivially equal to x of z. So y2 of z equal to x of z, which implies that y2 of n is equal to x of n, which is exactly the intuition, or basically when through the sketching process we already knew that they were different, and this is a more of a formal structure where we say that yes, they are indeed different.